Okay, so hi, I'm Casey. I'm the Chem 38 peer tutor for the College of Health and Human Sciences Student Success Center. And this is going to be a workshop just to review for your upcoming exam 2 that I know is coming up on Monday. Just in case you're not familiar with my tutoring hours, I put them on the screen. And if you need help like scheduling it, I'd be more than happy to help you go more detail after the workshop. But yeah, this is basically what we're gonna go over today, because I noticed that a lot of students have a more difficult time grasping these concepts. So we're going to go over bonds, the difference between ionic and covalent compounds, molecular geometry, and a little bit of polarity. With that being said, that also touches on Lewis dot structures. And then we're going to go over balancing chemical equations and stoichiometry and mole conversions. So I just want to start off by asking, like, you can just type this in the chat or you can unmute yourself real quick. What's the difference between ionic and covalent bonds? Does anyone know? Ionic is metal and non-metal. Yeah, correct, Samar. Covalent is two or more nonmetals. Correct, that's perfect. Okay, so you guys can write it in your notebook, or I forgot to mention, you can also, I will send a workshop survey link and you can enter in your email and fill out the survey, and I can email you a PDF copy of my slides. So just in case you want to review it over the weekend, if you miss something or just want to go back, you can totally do that. So I'll send that a little bit later in the workshop. So let me start writing. Okay. So you guys can type this in the chat. So ionic bonds are the transfer of electrons between, Samar said, metals and nonmetals, whereas covalent bonds are the sharing of electrons between two or more, or I guess a nonmetal and a nonmetal, or two or more nonmetals. So going more in depth with covalent bonds, there's polar versus nonpolar. So which one's the equal sharing of electrons? The equal sharing of electrons. Nonpolar. Yeah, correct, Caitlin. So just write. I have a question. Can you guys see the chat when I look at it? Like, can you see the chat right now or no? No. Okay, cool. So this is the unequal sharing of electrons, and then nonpolar is the equal sharing of electrons. So these Lewis dot structures of nonpolar will look more symmetrical, unlike polar Lewis dot structures. So can I erase the board now? Yes, you need a little bit more time? Yes, okay, cool. So let me, okay, so this is our first practice problem. So can anyone name this compound? No? No? Okay. So is it, okay, let's take a step back. Is it ionic or covalent? Let's launch this poll. So you guys can see the poll and you can click on your answers. We'll just see how everyone does on this one. Okay, yeah. Okay, so a lot of you guys said covalent, and that's correct. And Samar said in the chat that it's carbon tetrachloride. So covalent bonds are the ones where you have to remember that the subscript, the numbers on the bottom, they matter because that correlates to the prefixes, right? Like mono, di, tri, tetra, et cetera, et cetera. I would highly recommend memorizing the prefixes 1 through 10, I believe, 1 through 9, 1 through 10, for your test. And for ionic compounds, do the subscripts matter? Yes or no? No, exactly. Yeah. So in ionic compounds, the net charge matters, right? The charges of the metal and the non-metal, right? So they have to equal a net charge of what? 0. Perfect. Okay. So moving on to my follow-up question for carbon tetrachloride. Is this polar or non-polar? What's our first step on how to determine if this is polar or non-polar? What do we have to create? Yeah, perfect. Okay, so how many valence electrons does carbon have? 4. Perfect. Thank you. And then what about chlorine? Just a single chlorine? 7. Yeah, so there's 1 carbon, and then there's 4 chlorines. So how many total valence electrons do we have? You can use a calculator if you need to. 32. Okay, perfect. Thank you. 32 valence electrons. I just put B like that. Okay, so that's how many electrons we have to include in our Lewis dot structure. So which one is the central atom, carbon or chloride? Carbon. Perfect. Thank you. So carbon goes in the front, or in the center, sorry. And then we have Cl, 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 and Cl. And how many do we have? A single bond, a double bond, or a triple bond between these carbons and chlorine? Single bond. Yeah, perfect. Thank you. Okay, so I start off counting the bonds first. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. Does everything fulfill the octet rule? Yeah, perfect. Yeah, and it matches the 32. So this is the correct Lewis dot structure. And this one's pretty easy, especially things with carbon and then a 7A group with 4 of them. They're typically going to look like this. And you can see just by looking at the structure that this is nonpolar, like how forgot. Someone said it in the chat a long time ago, but yeah, this is nonpolar. Do you have any questions on how we got nonpolar? Because remember, this is the equal sharing, so it's very evenly distributed.
So how, like, do you look at like how we drew that? Because I'm still not sure how you determine if it's polar or non-polar.
Yeah, good question. So, like how I said before, this is evenly distributed, right? So covalent bonds are the sharing of electrons. So since chlorine, they're all the same element around carbon, they're going to have the same pull. And how is it? Okay, so this pull would be this, right? And the numerical value of the difference in electronegativity would be the same here, right? So they would cancel out. So it's kind of like adding vectors in a sense. Okay.
So if it was CL3, would it be would it be polar?
Yeah, because if we took this out, carbon would have a lone pair, right? A lone pair of electrons. So it wouldn't evenly distribute the electrons that we want to be bonded, right? So good question, because usually a big giveaway for making it polar is if it has lone pairs. If it has lone pairs, it's pretty much a dead giveaway that it is polar. For example, can I erase this? Is everyone cool with me erasing this?
Yes.
Yeah. So we can do the typical H2O, right? So H2O would look something like this, because we have 2 valence electrons here and 6 here, I believe. So we have 8 valence electrons. You always want to, that should always be your first step of counting how many valence electrons there are supposed to be. So you have 2, and the bonds always count as 2, right? So 2, 4, oh, yeah, 6, 8. Okay, 6, 8. So these 2 lone pairs here make it very unbalanced, right? Right? No? Yes?
Yes.
Yes. Okay, cool. So technically, if we're still staying with that vector analogy, it would look like this, right? So that vector is made up of going this way and going up. This one's going the other way and still going up. Since these two are going the opposite ways and they're the same element, they would cancel out, right? But it still has a net of going up. So that means it's polar. Does that make sense? Or is the vector thing confusing? Yeah, Caitlin, I just saw your chat. That's a perfect example of like they are literally like having a tug of war with a central atom. That's the whole electronegativity part. Yeah, that's a good analogy. Does anyone have questions on this?
Can you kind of further explain the vectors and how it like helps?
Yeah, so if the net vector results in anything other than canceling out, then it's polar. Does that clear it up a little bit, or still no?
Not really.
No? Okay, so let's see. So this right here, this arrow pointing right and pointing up, comes from this one, right? We broke down this vector of diagonally slanting this way, right? Because oxygen is more electronegative than hydrogen, right? Okay, so it would be the same type of pull, but the other way, because it's on the other side of oxygen, because Lewis dot structures, the electrons want to be further away as possible from each other because they're all negative. So if you think of a magnet, one side's positive, one side's negative. If you have two magnets on the both negative side, they repel each other, right? They don't want to be near each other. So they want to be as further apart as possible. So that's kind of the idea behind Lewis structures. Should we go like?
I got it now. Yeah.
Okay. So does anyone else have? I know that like whole vector thing is kind of confusing, but typically if it's like carbon with a 7A, halogen with a 4, it's probably going to be nonpolar. That's a shorthand way of doing it. If you see a lone pair, it's polar. Those are the tricks that I picked up from Chem 30A and Chem 1A. But we can do more practice problems. And if you still need a little bit further explanation, you can like set up an appointment with me and we can go more in depth on this. But for the sake of this workshop, I'm just gonna go ahead and go to the next one so we can still talk about it if we still need to. So I'm gonna go ahead and clear that. Okay, so my other follow-up question for carbon tetrachloride is still gonna stay on this compound. What's its molecular geometry? And of course, I don't expect you guys to memorize the chart, so I have it here. So we have this one, this slide, and the other slide. So how many domains are in this? And domains, I mean, let me quickly go ahead and redraw that. And pretend that all the rest of the dots are around it. How many domains are around carbon?
4.
4. Yeah, correct. 4. So we have 4 domains. How many of the domains are bonded, and how many are lone pairs? Yeah, correct, Julia. Yeah, all of them are bonded. There's no lone pairs. So going to the next slide. So automatically we can kind of cross out linear, right? Because linear is 2 domains. Oh, let me just make it as a table. 2 domains. Domains, lone pairs. I'll just do it for LP, and then bonded pairs. Oops. Okay. So we have 2 domains for linear. How many lone pairs for linear? 0. Yeah, correct. And then since there's 0 lone pairs and there's 2 domains, that means there's 2 bonded pairs because the lone pairs and the bonded pairs have to equal how many ever domains there are. Domains just mean like area of where electrons are. So going on to trigonoplanar, it can't be this because there's 3 domains, 0 lone pairs, and 3 bonded pairs, right? So what about bet? How many domains? 3. And there's two vents. So there's another one on the next slide, so don't worry. So we have 3 domains. How many lone pairs? 1. And then that means there's 2 bonded pairs depicted as lines here. And then the lone pairs are the circles. Sorry if my drawings aren't that good. But does anyone have questions on how we kind of filled in that chart? Nope. Okay. Let me go ahead and do this second one. Clear this. Okay, so it's not any of the first slide, so it has to be on this one, right? So domains, we'll just put D, L, P, and then bonded pairs. Okay, so tetrahedral, how many domains? 4, correct. Lone pairs? 0, and then bonded pairs? 4, yeah, correct. So seems to me that Caitlin was correct. It is tetrahedral because it has the 4 bonded pairs. So just filling out this chart, trigonal pyramidal has 4 domains. How many lone pairs? 1. And then that means this has 3 bonded pairs. And this is the other bent, which is the H2O one, right? This has 4 domains. How many lone pairs? Correct, Vivian, 2. And this means that this is 2. Okay, does anyone have any questions on molecular geometry chart of what a domain, what a lone pair, what a bonded pair, anything of that?
Yes. So can you give us an example of what like a formula of a triagonal pyramid, however you say it, will look like?
Yeah, it actually is the next one. So we can do that now. So red color. Let me do this. Pf3. So what is Pf3? Ionic or covalent?
Is it covalent?
Yeah, covalent. Typically loose structures are only for covalent. I'm pretty sure ionics don't. I don't think ionic is for loose structures. So yeah, Pf3. So we have a covalent bond. So which one is the central atom? P or F?
P.
P. So we have P here. 1, 2, 3. Have 3 Fs. Doesn't really matter if you want this F to be on the bottom. It doesn't matter. So we have how many valence electrons in total?
Is it 12?
12. Okay, so we have how
Because
many?
I think phosphorus has 5
5.
and fluorine has 7.
Oh. So what does it equal? 21 plus 5.
Oh, 26.
Perfect. 26. Oh,
Right? 26.
valence electrons. Okay, cool. So we have to get 26. And we have 2, 4, 6 already. 6. And you always want to have the non-central atom to fulfill the octet rule. That's more of the priority versus the central atom. Not sure why, but it's just how it is. So we want to do 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and that last pair goes right here. So technically everything fulfills the octet rule, right? This has 8, this has 8, this has 8, this also has 8, except this one is not a bond, it's just a lone pair. So since this has 4 domains, right? 1, 2, 3, 4, and it has one lone pair, which is the one connected to the P. So this is the lone pair, lone pair and bonded pair, they always relate to the central atom. And then the rest would be the 3 bonded pairs. Does that give a good example of trigonal pyramidal?
Yes,
Yeah.
that made a lot of sense. And I also learned more about the Lewis dot structure and how to like write it out. So yes, thank you.
Yeah, no problem, no problem. Anyone else have any questions on that? And that's kind of messy, but hopefully everything flowed well. But yeah, let me go ahead and clear this out. Yes, yes, Esther. Trigonal pyramid. Going on. I already did this. We just did this, so I'm just gonna go ahead and skip this one. So going back to this, to the polar or non-polar, let me redraw it really quickly. P, F, F, F. Okay, so pretend, okay, I guess I could do this too. Yeah, Caitlin, it's polar. Yeah, remember that if it has a lone pair, it's probably polar. It's definitely not even because this one doesn't have a bonded F to it. Maybe if this was a 4, then it would be polar. But yeah.
So it's non-polar?
It's polar.
Oh, polar because of the lone pair, right?
Yeah, exactly.
Okay. If it was PF4, it would be polar.
Non-polar. Non-polar is, yeah, it's okay. You're good. You're good. You're good. It's okay. Polarity is a hard concept.
Sorry, once again, so this one right now, is it polar because it's uneven?
Yes, exactly.
Okay, thank
Polar,
you.
yeah. So let's do that. So is this ionic or covalent? NaCl.
It would be ionic.
Yeah, exactly. Yeah, because Na is a metal, right? So we don't need to worry about nonpolar, polar, because it is ionic. So what charge is Na?
1 plus.
Exactly. So let me Na plus, and then Cl has to be what charge?
-1 charge.
Yeah, -1. So I'm not sure if you guys know the like trick. I don't know if she told you, but you guys can tell what charge, where we got the charges for the for these by, it only works for the representative groups, so the A group. So this, if it's in the 1A group, it has a +1 charge, +2 charge for the 2A, +3. This one's kind of a weird one. I think it's +4. But this one's kind of weird. So honestly, we're just
Yeah,
gonna.
that one was like ±4, right?
Yeah, that one. Yeah, Yeah, that's why I was like, I mean, you kind of just, we'll just keep that as an X because usually she won't put anything there, so you can kind of not worry about it too much. So we're gonna just mirror it, but the opposite way. So negative, -3, -2, -1. This one we don't count because they're noble gases. They already fulfill the octet rule. They don't really like bonding because they need more energy to like bond than just to stay by itself. For the transition group and the intertransition metals, they're kind of, they don't really follow this pattern. So it's kind of unfortunate, but that's how the typical charges come from. Any questions on that?
Yeah, I have a question. So because group 4 is kind of weird, what if she gives us like like an equation or like something that we have to balance, and the carbon is there? So do we like have to find out how many charges it has, or?
Usually when there's a carbon in like in the chemical reaction, right? It's a non-metal, right? So it'll never have a +4 charge usually. I think that you can kind of get away with it because you know how there's a staircase, right? There's like a non-metal that separates the non-metals and then semi-metals and then metals. So metals, remember, they form cations. They produce positive net charge. If it acts as a non-metal, it's an anion, which produces -1. Does that kind of help? Kind of.
Yeah, thank you.
Okay, cool. Okay, let me clear this. Okay, so is HCl ionic or covalent? We have 1 vote for ionic. Anyone want to agree or disagree? Covalent. Got 2 for covalent. Okay, so okay, I appreciate the honesty. Okay, so hydrogen, although it's in the 1A group, which is the like metals, right? This is still a gas, so it's a non-metal. So if this is a non-metal and this is a non-metal, it has to be covalent. And then to be more specific, does that look familiar? Is there like a specific type of solution it creates? Does this look familiar at all? With an H in front?
Is it an acid?
Yeah. It's one of your strong acids. So acids are usually indicative of an H in the front, whereas bases end with what?
OH.
Yeah, a hydroxide. So this H has a what charge? Yeah, a +1 charge. And then OH has a what charge? Yeah, negative. Okay, so if we were to do Ca plus OH, how would we write that? Because this is a -1 charge, right? Ca, yeah, perfect. Thank you, Samar. So it's CaOH. You have to put that parentheses there because it's a polyatomic ion. So it's like you regard it as a unit. Then we put the subscript here. What would happen if we put a coefficient instead? What does that mean? How many hydroxides are there? How many OHs? 4, exactly. Okay, perfect. Yeah, because this would distribute. That's pointing the 2. It would distribute. So we'd have 2 calciums and then 4 hydroxides because there's already 2 here. Okay, so that's going to help you with our next section, which is balancing equations. I think we have one more actually, but I'm not sure. Let me see. Oh, by the way, is it polar or non-polar before we move on? This one we have to kind of use the electronegativity type. Polar, yeah, exactly. So when we make our Lewis dot structure, right, it would look something like this. Oh, all this 2, 4, 6. Okay, so it would look like this. So since hydrogen only has one electron and it's already sharing this with chlorine, this has so much more electrons, right? So this is way more negative than this side, right? Does that make sense how we got polar? Yeah.
That helps a lot.
Pardon?
Oh yeah, I was saying that diagram helps a lot.
Oh yeah, no problem. Yeah, okay, cool. Glad that it's helping. Okay, so let's move on to the next one. Okay, so balancing chemical equations. So if there's an H in front, I don't know if it'll always be polar, but I guess it depends on what the structure looks like. Sorry, that's kind of a hard question to answer. I wish I could say more than it depends, but for that specific HCl one, it is polar. I'm sorry, I can't for sure say it's always. But if it does come with like two, if it just comes with 2 elements, so like a binary compound, you can look at, she'll give you electronegativity chart. You can see which one's more electronegative or not. And if it is, I believe she has it's part of her notes of like the difference of electronegativity classifies it as polar or non-polar or ionic. But that's different. Okay. Let me go ahead and, just because I saw the time, let me go ahead and send in the thing just in case anyone has to go. I'll send in the workshop thing as well as the link to the YouTube. I just X'd out my tabs. Okay, give me one moment. I'm sorry. You can use this for like a water break or something. But yeah, do you guys feel like ready for your guys' test? Like, how do you guys feel about your test? You know, feel like confident, kinda, like.
I feel if I'm legit, I don't feel confident at all. I got 3 days.
I mean, that's 3 days. You got 3 days, which is a lot of time. Yeah, I know you can do it. Like, you got 3 days. I mean, I believe it's only how many chapters? 3 chapters, maybe.
Yeah.
Yeah.
I mean, like, I feel like, last midterm for real, I didn't, didn't do well for real. So I'm just like, so now I'm like, I'm kind of like in scramble time, but also too, I'm starting to understand like some stuff, but at the same time, I don't even know what I'm doing.
You have like, I think it's 4 or 5 weeks left of the semester.
Yeah.
So if you didn't do too hot on the first midterm, you definitely got the second midterm to bring up your grade, as well as all the lab that kind of like fluffs up your grade as well. So I believe that you can bring it up. I wouldn't stress too much about it. Just keep studying. Go to the, I think the lectures are synchronous, right? I'm pretty sure.
Yeah.
Yeah, so I think that if you do need more support, I could definitely, we could set up an appointment and we could do one-on-one like practice problems for sure.
Sure.
So okay, let me go ahead and screen share. So you can search up CHHS, SSC, SJSU, and this channel will pop up, and it's our center. You just hit videos, and once I upload this, it'll be like the first one here. But just in case you guys want the link instead of typing it all in, I'm gonna go ahead and chat, like do it through chat as well. Okay, cool. So after that momentary pause, okay, let me go ahead and go back to presenting.
Is there a way that you can, is there a way you can share those slides or no?
Yeah, actually when, I'm not sure if you were here in the beginning, but I said that if you guys do the workshop survey and then you type in your email address,
Yeah.
I will email you guys the PDF version of all the, like the entire slides presentation.
Sure.
So yeah, the only thing is that it won't have the answers, so you'd have to like,
It's all good.
yeah. Okay, cool.
It's all good.
Yeah, for sure. Okay, so going back to chemical equations, what is our first step? Like, how do you guys approach this first? Any idea? No clue?
I try to like count how many of each unit is present already in each side.
Yeah, perfect. Okay, yeah. So I kind of make a line separating the two, reactant and product side. And then I list out each element. We want to always try to keep the polyatomic ions together. We kind of regard them as a unit. It just makes it easier unless it's broken down. But since this is a nitrate and this is a nitrate, we know that it doesn't like break down into separate nitrogens and oxygens. So we do the same thing here, CaCl, Ag, NO3. I kind of like to line them up in the same order just so we can see the numbers better. So how many calciums do we have here?
We have one,
Yeah, 1. And then Cl?
2,
Ag?
1.
1,
1, perfect. And then nitrate?
3. 1.
Yeah, 1. Okay, close. Yeah. 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 So for on this side, we have
1.
We have 1.
2. Oh wait, sorry. 1.
We have 1.
1.
We have
1.
We have
2.
2.
Perfect. Okay, so which
Wait,
one?
so why would, oh, so NO3 will be 2 because of the 2 that's next to the parentheses?
Yeah, right here.
For sure.
Okay, so which ones you can see right off the bat, which ones aren't balanced?
Are you saying
NO3.
balanced or not balanced?
Which ones are not balanced?
Oh yeah, NO3
NO3 and Cl.
and Cl.
Let me think about it. NO3 and Cl. Okay, so I like to attack the polyatomic ions first, just because they're the most complex part about it. So, do you want to add more nitrates to the reactant side or the product side?
Reactant.
Reactant. So, what number do you want to put in this coefficient right here?
2.
1. Oh,
2.
or 2.
Okay, we're gonna do 2 because we already have 1. And so that makes this distribute, right? Makes it distribute to that. So we have 2 more silvers, 2 more nitrates. This stays the same. What about for this side? Does that match it now or not yet?
Not yet.
Not yet.
Okay, so what do we have to manipulate here? Which elements?
Cl.
Cl.
Cl and Ag.
And luckily for us, they're together right
Hey.
here. And then so what would this number be in the front?
2.
2.
Perfect. So checking back, we have 1 Ca, 2 Cls, 2 Ags, 2 nitrates, 1 Ca, 2 nitrates, 2 Ags, and 2 Cls. So they all match up. So this is balanced. Any questions on how we did that? No?
No, I mean, that makes sense to me.
Okay, cool. So I'm gonna go ahead and clear it. Okay. So let's do this one. Does anyone know what type of reaction this is?
Heck no.
Okay. It's a acid-base titration problem. I believe it's one of your types of the types of chemical reactions you guys have to know about, like the redox reactions and like double replacement ones, right? So this one's we're just balancing this one. So doing this again, we have the H, the sulfate, the potassium, and the hydroxide. Remember, this is a polyatomic ion. We consider that as actually, just kidding. Just kidding. We're gonna have to break it down because you see here, there is no hydroxide in this one or this one. It broke down into water, right? So for this instance, we're gonna have to break that down, and that's typically for acid-base titrations. I totally forgot about this. And that H2O comes from this hydrogen and then this hydroxide. So there's, I don't want to give it away, but let's pretend there's no 2 here. So that's where the H2O comes from, right? H2O. But anyways, we're just gonna go back. H, SO4 stays SO4, K, and O. Okay, so just listing them down for the reaction side. Go ahead. Anyone?
So it'll be 2, 1, 1, and 1. I mean, it would be 2.
No, it's 1. It's 1. I think does anyone have any objections to this?
Wouldn't H be 3?
Yeah. So I think you just forgot to add this one because this one, I said we were going to break this one down just because it's just this type of problem. Sorry about that. Anyways, for the product side, anyone want to take a guess at it?
2 for H.
Mhm.
1,
Mhm.
2,
Mhm.
and 1.
Perfect. Okay, so which ones do we want to kind of mess with?
K.
Okay. So on this one, what do you want to put in the front?
A coefficient of 2.
So we put 2 here. What does that make the rest of the elements?
O would be 2 and H would be 4.
And this one stays the same. So does that match?
No.
No. Okay, so what do we want to fix?
Water on the product side.
Okay, so what do we want to put on the coefficient? For the
A
coefficient?
2.
A 2, okay. So that makes these we never touch, so that stays the same. How many hydrogens?
4.
Mhm.
And 2 oxygen.
Perfect. So this all matches up, balances perfectly on both sides. Any questions on this one?
Low key, I kind of got confused
Okay.
on the reactant side. Is that what you're talking about? On the right hand side?
On the side?
Yeah.
The product side?
Yeah, I mean my bad, the product side.
It's okay.
Because for H there was only 2, but but you also said they're gonna break it down inside because I thought when the H was there, never mind. It was the O on that side of where we put 1, but I seen the 2 O's and I was like, oh, I thought of 2, but I was wrong.
Okay. So do you get it?
Yeah.
Yeah. Okay. So okay. Yeah, I know the breaking this down, the OH kind of confusing, especially because I just introduced that we put the polyatomics together. My bad. I just wanted to expose you guys to like all the different types of questions that make it come up, just so you guys have a variety. So yeah, any other questions on this? No? Okay. I'm gonna go ahead and clear it. Go to the next one. Okay, so just looking on time, how do we feel about chemical equations? Or do you want to do more practice or move on? We'll take a vote. I think you can put reactions and like look at yes or no. So if you want to continue doing balancing equations, pick yes. If you want to move on, click no.
What was the next thing that we were going to go over?
Stoichiometry. So that's
God.
like mole conversions.
I think we should move on.
Move on. Okay.
Yeah, that's cool. I'm cool with that.
Okay, cool. So I'm gonna go ahead and move on. But like I said, if you guys want to do the survey thing, you guys can have this free practice. I think there's only 2 more. Okay, so just starting off with stoichiometry and mole conversions. What is Avogadro's number? So we have the times 10 to the 23rd. I just couldn't find the 23rd part. What's the first part? Yeah, 6.023. Okay, perfect, Caitlin. 6.023. I forgot to add another dash. Don't worry about it. So that number is over 1 mole. And the units for this can be either particles. Sorry if my handwriting is bad. Particles. What's it called? Molecules. X atoms, and where X is any element, so like carbon atoms, hydrogen atoms, et cetera, et cetera. I think there's one more unit factors, unit something, I don't remember. I don't remember, but there's unit something. I forgot. Unit, does anyone know by chance? Unit. No, I don't know. I didn't see any on her recent one, so maybe she took that one out. I'm not really sure. But anyways, this unit, so this is essentially a conversion factor, right? And this is useful because for every element on the periodic table, there's an atomic mass. And that atomic mass, you typically see it as grams, right? But it's can also be written as grams per mole. Oops. I don't know why I did that there. Grams per mole. So if you see here, this can also be a conversion factor, right? So if it's a single element, just like beryllium here, you would just write the atomic mass on this side, right? On the top side. And then if it is a compound, so like CO2, you would have to find the molecular weight or the molar mass. So you would have to add the mass, the atomic mass of carbon, one carbon. I'll just put X. And then the atomic mass of two oxygens. So there's 2 oxygens and then whatever, I'm pretty sure it's 16. This is 12. But you would consider all that, you would add all of them up and then put them here. And it'll make more sense when we apply them to actual problems. But what I'm trying to get across is that it's just like your normal conversion factors, like when you had to do meters to kilometers and stuff like that. It's just a different unit. Any questions on this?
No.
No? Okay, cool. Okay, so I'm gonna clear this. Okay, so we're gonna start with okay, thank you, Vivian. Formula units. Okay, sorry, that was the other thing. Thank you so much. That was gonna bother me forever. Okay, anyways, so how many Be atoms are in 2 moles of Be? So what is the given in this problem, right? What's the given?
2 moles.
Yeah, so this is the given. So we have 2 moles Be. What would be the conversion factor? Where would 1 mole be? On the top or the bottom?
The bottom.
Bottom.
Yeah, we want to cancel out, right? And actually, let me kind of make a little bit more space. 1 mole of Be. And on the top, what would it be? Something Be. Something here, right?
Would be like would it be the 9 number or no?
Yeah, it's the 9 number. So we're just gonna do 9 just so the math can be easier. So we have 9 grams, right? 9 grams of Be per 1 mole of Be. So this would get rid of the moles, but that would leave us in grams. And what do we want?
Grams. I mean, not grams, but atoms.
Yeah, we want Be atoms. So this is going to be a multi-step conversion problem. So we're going to have another conversion factor. So, oh, I'm so sorry. I'm so sorry. Wait, I screwed up. My bad. Wait, that's not on the top. That's not on top. That's not on top. My bad. No one caught that? No one caught that? Okay, 1 mole of Be. What would be on the top? I forgot. This is a one-step one. One step.
Avogadro's number.
Yeah, I'm so sorry.
I had thought of that, but
I was
then you were like
confused.
denied, and I was like, oh, okay.
I'm sorry. I'm so sorry. I'm sorry. That's on me. That's on me. My bad. My bad. I can't believe no one like said anything. Okay, anyways. So this molecule, and then you would have the number of Be atoms. Oh, sorry, that's Be atoms. Sorry. I'm sorry. It's Friday. It's Friday. But yeah, you would just plug that in the calculator, and you would have the answer. Anyone want to?
Would there be a time where you go from moles to grams to atoms?
Yeah, that's what I thought this one was, but I think that's a different problem, and I just was ahead of myself. Sorry.
Okay.
But yeah, I do have a problem like that. It's just not this one. I just played myself. Okay. But yeah. Do you guys want to go over just check your answer, or are you guys good with just plugging this in? Up to you guys. We have less than 30 minutes.
I mean, we already have the equation there, so.
So does anyone want to give me the right answer?
It's 1.20 times 10 to the 24th.
Yep, 1.2 10 to the 24th. This was,
Wouldn't sig fig apply and it just be 1?
yeah, I was just gonna say that. Yeah. And she's got that because there's only one sig fig here, right? So if it was 2.0, then it would be that. So good catch, good catch. So any questions on this one?
So it's 1.2 or no?
No, it's just 1. 1 times 10 to the 24th. Because there's only one sig fig. Okay. So let me go ahead and go to the next problem. How many grams of Be are in 2 moles? So we start off with 2 moles again. Then what's this conversion factor?
At the bottom, it would be 1 mole of Be, and at the top it would be molar mass because that's in grams, and that would be, I would usually do 9.01, but yeah, 9.
Yeah, I just want like the calculations a little bit easier. So yeah, that is just, this is the one that I was thinking of, but not really. Okay, so yeah, this would be 18. I'm so sorry. 18 grams. But if we were to consider sig figs, what would this be? What would this turn into?
20.
Perfect. 20 grams of Be. There you go. Any questions?
Do you know if on the exam she would have either 18 or 20?
For like the answer questions?
Yeah, like based on the sig figs, like if we choose 18, it would be wrong.
I'm gonna guess probably because they want us to be careful of that, but
Yeah, I would definitely always consider sig figs. but I don't have access to the test, so I don't know. But I did take her class, and to be honest, it wasn't ever tricky like that, in my opinion. But I also took it in person 2 years ago. So I'm not sure if she made the test harder. I would imagine not, but I mean, as long as you know how to apply the sig figures, I think you'd be fine. But yeah, I wouldn't say to worry too much, because like I don't know how you guys felt about the midterm, but it does. Her tests do replicate her lecture check-ins or something like that, on her quizzes and like the practice exam problems that she gives you. So it shouldn't be like, I know that some students are scared that she's gonna like have a tricky question that she's never asked before, but she doesn't pull tricks like that in her tests. I promise.
For sure.
Yeah. Okay. So this is the one. Here's the multi-step one. So again, we have the given is 4.8 grams of BE. What would be the next step, I would say?
Changing the grams to mole.
So would the grams, the molar mass be on top or bottom?
On the bottom.
The 9 grams BE, 1 mole of BE. Okay, so that gets rid of the grams. And then what about this conversion factor? Because we're not yet at atoms.
Avogadro's number?
Yeah, and will his number be on the top or the bottom?
The top.
600 times 10 to the 23 BE atoms, then 1 mole BE. So then that mole crosses off and we're left with BE atoms. And remember, when you're doing unit conversions, if it's on the bottom, you have to divide. Divide. If it's on the top, you have to multiply. And then you get the answer. Any questions on how to get to BE atoms? Anyone have the answer to the BE atoms?
I got 2.65
2.65
times 10 to the 23rd, sorry.
times 10 to the 23rd. Okay. Is this the
For sig figs, there's 2, so it would be, well, it was originally 2.648, so it would be just 2.6 times 10 to the 23rd, I think, because 4.8.
Okay, so 2.6. Okay. Anyone have any objections to that or agree to that?
I got 3.2.
Yeah, I think you accidentally put 4 divided by 9, but it's actually 4.8.
Oh yeah, that was my bad. Yeah.
It's 3.2.
Okay. 3.2 times 10 to the 23rd. 23rd still correct or different?
It's still correct.
Still correct? Okay, cool. Any questions on that?
Would that be 3 times 10 to the 23rd because of the sig figs of the mole and the grams? Or is that just 3.2?
It would just be 2 sig figs because it's given here. This one you wouldn't really consider because it's a constant, right? A unit conversion factor. So you don't consider that as sig figs.
Oh, okay, got it.
Perfect. So, and same with the molar mass. You don't consider that because it's a given. You could add the entire 9 point everything. That would be a more accurate answer. But just for this workshop's sake, I just put 9. But yeah, good question. Okay, so we're getting a little bit more into a little bit more difficult because there's a binary compound instead of just a single one. So how many O atoms are in 10.2 grams of carbon dioxide? So we have 10.2 grams of carbon dioxide. So what do we do to turn that into O atoms, oxygen atoms?
You first want to calculate the mass of carbon dioxide first. So you add basically 12.01 plus 15.99 plus 15.99.
And what does that equal?
It's like about 44.
Okay,
I think
44 grams. Okay, so the top is what?
1 mole CO2.
1 mole CO2. Okay, so now that we got into moles of CO2, what do we do now? Get rid of the grams. We're at moles. What do we do now? An easy thing.
Isn't it mole ratio?
Yeah, the mole to mole factor. So what would be directly diagonal from here?
Is it 1 mole CO2?
Yeah. And you know that because it has to cancel out, so it has to be mole of CO2. So we're interested in oxygen though. So what would be on the top?
2 moles?
2 moles of O. And she got that 2 from this subscript here. So technically this is saying that there's 1 mole of carbon per 1 mole of CO2. And then oxygen has 2 moles of oxygen per 1 mole of CO2. Anyone have questions on how to get the mole to mole factor? Okay, so we're gonna cross off the mole of CO2, mole of CO2. Now we're left with moles of oxygen. So we're still not quite there yet, but we're really close. So what is the next step?
Is it multiplied by Avogadro's number?
Yeah, so we drag down this unit here. Mole of O, 1 mole, right? 6.023 times 10 to the 23rd O atoms. I can't fit it, but that's how you get all the way to O atoms from all this train, right? Any questions on that, like multi-step problem? Okay. Okay, does anyone have an answer for the O atoms?
I got 2.80 times 10 to the 23rd.
So the third, okay. Anyone agree, disagree?
I agree.
You agree? Okay, cool. Okay, so clean this. Okay, so seeing that we only have about less than 10 minutes or less than 15 minutes, I'll let you guys pick. Do you want to do this problem with H2 and O2 or with multiple ones, or Fe plus O2, or this one, the very last one? Your pick. You guys can pick. I think we only have time for one.
The water one.
The water one? Anyone want to guys vote on it? One, this water one, this iron oxide one, or this double replacement one?
I'm cool. I'm cool with whichever one.
Everyone? Okay. So we can do the water. Oops. Oh, that is the end. My bad. Okay. You do the water one. Okay, so we have how many moles of O2 are needed to react with 5 moles of H2. So this is the actual stoichiometry part, right? I think we need this. Wait. Okay, wait, this one. Sorry, I meant 6 moles, but it's the same question, just I did a different one. But we need need this part, so I'm just gonna do this one. So how many, what's the first step? So we have 6 moles of H2. Do you see anything that we have to do first before we do anything?
You have to balance the equation.
Mm-hmm. Okay, so before we do that, H and O. H and O. So for the reactant side, we have how many?
2.
2. Mm-hmm. And then oxygen.
2.
Mm-hmm. And then this one, this side.
2.
Mm-hmm. And then for oxygen.
1.
1. Okay, so we see that oxygen is the one that we need to fix, but there's not really a singular oxygen. So we're gonna have to mess with the hydrogen as well. So which one do you want to add a coefficient to? HO or H2O?
H2O.
Okay, and what number do you want to put in here?
2.
2. That makes a 4 and a 2. This one already is lined up, so we don't want to add anything here. We want to keep this as a 1. So that means we have to put a what here in the front?
2.
2. We have 4. So that's what we have. It's correct. It's balanced. So now we can proceed with our problem. So going back to 6 moles of H2, and we want moles of O2. So what do we do? What's our unit conversion factor? Or fusion, yeah.
Did you use the formula for the mole ratio thing?
Which formula?
Or the equation above, right?
Mhm.
So it would be 2 moles of H2 is 1 mole of O2.
Mole of O2? Oh, O2, sorry. You see where she pulled those numbers from? So 2H2, the coefficient, and then there's the 1 that goes for the O2. Okay, and then so this gets rid of the moles of H2, and we are left with moles of O2. So 6 divided by 2.
3.
Yep, 3.0 moles of O2. Okay, pretty easy with the mole to moles. Okay, so taking a little step. Okay, a step further. Okay, let's see. how many moles of H2 are produced from 5 grams of H2? And we had already done this, so we're just gonna add that there. 5 grams of H2. Okay. What do we plug in here? What do we know is going to be on the bottom?
2 grams.
2
Or is
grams.
it 1 gram?
It's 2 grams. Yeah, H2.
And then 1 mole.
1 mole H2. Okay, so she got that 2 grams because there's an atomic mass of 1, but there's 2 hydrogens, so she times it by 2. Okay, perfect. Okay, so we have grams of H2 canceled out. Next step is what do we bring down?
The 2
1
mole.
mole.
2 moles of H2. She got this from the equation right here. There's 2 moles. And then we're interested in moles of H2O. So we're gonna have to look at your here, right? So 2 moles H2O, which is luckily 0, or not 0, 1, sorry, 1, right? So this cancels out.
I have a question. When do we look at the coefficient versus when we look at the subscript?
The subscript, okay, so the subscript matters when we're doing the molar mass. That's one of them. The subscript matters when we're counting how many hydrogens are in this problem, right? When we're balancing the equation, right? The coefficient is the one where it relates to the moles. So that's where you find all the multiple factors.
Oh, okay.
Okay, good question, good question. Okay, so I think we are left with moles of H2O, which does answer our question. Anyone have a quick answer?
I got 2.5.
2.5. 2.5 moles of H2O. Anyone agree, disagree? Okay. Well, it should just be 5 divided by 2 because this is just a 1. So yeah, 2.5 is right. Let's do our last problem. How many grams of H2 are required to produce 12 grams of H2O? Okay, so putting this back in here. 12 grams of H2O. What do we put down here? What do we need to convert this grams of H2O into?
Grams?
Moles.
Yep. Oh,
Moles? Yeah, moles. So grams of H2O per 1 mole H2O. So
Would
how
it be 36 grams?
36? Okay, and you got that from?
There's 2 oxygens. I usually just round to 16.
Mhm.
And then 4 hydrogen.
Oh wait, yeah, 216 from here, right? Plus,
Or is it just
oh wait, no.
2 hydrogen?
It's 1 mole of H2O, right?
1 mole of H2O. Sorry. So it is two hydrogens plus 1 oxygen.
Oh, okay, then it would be 18, sorry.
Yeah, no, it's okay. This would be 18. Okay. Anyone see any have any questions for that? Where we got these numbers? H2O. Okay. So we can go ahead. And is orange hard to see for you guys, or is it okay?
It's okay, but it looked better in red or a different color.
Okay, cool. So let me change it. Thank you for answering. So we got rid of the grams of H2O. We want to bring this down, right, to moles of H2O. What would be in the front?
Is it 2 moles?
Yeah, 2 moles right here. Got that from the equation, 2 moles. And what are we interested in? What's on top? What are we trying to?
Is it 2 moles of hydrogen?
2 moles of H2 right here. And then are we done? Did we get to our desired unit or not yet?
Not yet.
Not yet? Okay, so we have to do another step, bringing down this 1 mole of H2. What would be on top? What would be what we want?
Avogadro's number?
How many would that get us to grams?
2 grams of H2 on top.
2 grams of H2. We want the molar mass, right? So we wouldn't use the Avogadro's number unless it's asking for the number of H2 atoms or molecules, particles, or formula units. So if it's not asking for any of those units, then we wouldn't use Avogadro's number. So we got rid of the moles of H2, and we finally got 2 grams of H2. So H2, anyone want to answer that? So 12 divided by 18 times 1 times 2. .33. Did anyone else get 1.33? That's what I got. Okay. Or it's you got, sorry, 1.33. Perfect. Perfect sig figs. Okay, cool. That is the end of our workshop, just because I saw the time and I'm sorry we didn't get to finish. We only had 2 more problems plus the other 2 that we skipped, but I mean, I think did you guys think it was helpful? Let me know in the workshop survey, and if you guys have any requests for my final exam workshop, you can also put that in the survey on comments or something that you guys would like to know. Thank you, Esther. But yeah, I know that finals is coming up. I definitely know that my workshop for this class is going to be on May. Let me go get the flyers so I don't get it wrong. It's on Dead Day. It's on Dead Day. I'm not sure if you guys are familiar with the term Dead Day. It's it's the day after we stop all the classes, and it's the day before finals begin. Give me 1 second. Okay, cool. Okay. Kind of too big. Okay, so here's the information. I know that Zoom links are more easy to click on, but don't worry if you want the Zoom link. It'll probably be emailed to you when we start actually marketing everything. But if you want to like save the date or something, you can screenshot. But yeah, other than that, I have nothing else to say. If you guys want me to resend the survey link and the YouTube link, please let me know because I know it probably is far down far down the chat box. But yeah, you guys are free to go. If you guys have any like extra questions, feel free to stay back and ask me. Yeah.
So I'm trying to copy the YouTube links and stuff right now.
Oh yeah, no, for sure. Let me resend it just in case, so you don't have to like scroll all the way back up. So that is the Google form for the survey. And this is the YouTube channel link. No problem.
I had a quick question. So do you think her exams are like pretty straightforward, like her final and everything?
Yeah, there wasn't, I took it as like a freshman, like my first semester, and I thought it was like, I was super anxious, but it was really like if you did all her lecture, it's called a learning check, I think, not lecture check, learning check, and her quizzes, they're pretty like similar format, similarly worded. But yeah, I don't think it's tricky in any way because she does want you guys to succeed.
Okay, thank you.
No problem. Thank you guys for coming.
Just a
Sure.
quick question. What would you say is the best way to study?
The best way to study, chemistry is one of those classes. It's kind of like those math classes where you have to like practice, do practice problems instead of like just like reading the book. I would say that for your polyatomic ions and like your strong acid bases, the things that you have to like actually memorize, I would definitely use a flashcard, and I would recommend not leaving that off, putting that off, because there are a big chunk of things you have to memorize. But yeah, mostly how I studied was doing practice problems like over and over again. If you want, like I could give you practice problems if you make an appointment with me, specifically on the topics you want to work on. But yeah, does that answer your question?
For sure. And then you said that people